So meta science is really science about science. How do we use the scientific method to improve the institution of science? Because science is an institution. Science is produced by scientists who normally go through a very structured training process. Science is produced usually in professional and academic journals. It's read by other scientists. It is generally funded by the public, though there is a lot of private industry in science. But really, the goal of meta science is to use the scientific method to improve how we do science and to make science advance more efficiently and to reduce some of the negatives. So it's interesting because a lot of the issues that meta science discusses have sort of been discussed for centuries now. So one of the key things that meta science tries to improve is replication. And replication is a pretty simple idea. If I go run an experiment, you should be able to go run the same experiment and get the same or similar results. And that begs the question, how do you define the same or similar results? And that brings in different statistics like effect sizes and measures of statistical significance like p-values and such. But the point is that evidence has sort of accumulated over the past 10, 15 years that a lot of published research across fields doesn't replicate. And so people ask the question, like, this is a problem. Like, the public is spending a lot of money on science. And if that science gets done, it gets published, and then we try to build on it. And then we find out that original research wasn't actually correct. That's a lot of wasted time, money, resources. So what can we do about that? And so some of the issues that meta science discusses are the incentives of science, the incentives of academic science. So Chris Chambers, who is a professor at, I think, the University of Cardiff, he has these really excellent slides where he'll show sort of like the wheel of the scientific method, where it's like observe a phenomenon, come up with a question, develop your question into a hypothesis, go collect some data, analyze your results, and report what you found. And so he asked the question, which part of this wheel, which part of this process should a scientist have the least control over? And the answer is the results. Like, a scientist chooses what question they ask, they design their own experiment, but they don't have any impact on what the results are. The data are supposed to speak for themselves. And then he asked the question, what part of this process is most essential for having a career in science? And again, the answer is the results. So immediately you see this contradiction that can lead to a lot of problems. So to have a career in science, generally you have to win grant money. And to win grant money, you have to publish papers. And the way that the publishing ecosystem works is, to publish a paper, you need to have something exciting to report. You need a positive finding. You have to discover something. And so science is hard. And what happens when researchers do an experiment and their theory isn't supported? They don't get the really exciting positive results that they were potentially hoping to get. Well, then the story can get a little bit ugly. So some people, like there are cases going on right now with the president of Stanford, who just resigned because he was discovered to be producing fraud. He was inventing data out of thin air. He was fabricating data. That is extremely serious. Anonymous surveys of scientists show that outright fraud is actually very rare, which is wonderful. It's a very good thing. We don't want scientists just inventing numbers out of thin air and then, publishing based off of it. But what anonymous surveys do show is that this sort of bucket of gray area practices known as questionable research practices, or QRPs, some of those are actually very common. So we can talk about what some of those are. One of them is selective reporting. And just to give an idea of what that is, let's say you have a hypothesis, you do 10 experiments to test it, 5 of them support your hypothesis, 5 of them don't. Great. Write the paper about the 5 that supported your hypothesis, leave the other 5 to the side. One is called harking, or hypothesizing after results are known. So you have a hypothesis, you run an experiment, you get your results, your hypothesis is not supported. That's okay. I'll just write the paper with a new hypothesis that is supported by the results that I got. And that's very problematic. Another one, which is sort of well known, is p-hacking. So p-hacking is sort of running lots and lots of analyses on your data, and the ones that give you a statistically significant result, which typically means a p-value less than 0.05, you publish based on that. You publish the findings that are significant. The ones that are not significant, you don't publish. And it's kind of wild because a lot of these problems have been known for decades and decades and sometimes centuries. So there's a paper, it's by, forget the first name, I think the last name is Sterling. It came out in like 1959. And he says, it's quite worrisome that the literature is filled with so many positive findings because the null findings are not published. And so if somebody does an experiment and the hypothesis is not supported, well, nobody knows that. Mm-hmm. So you might have a whole bunch of experiments that are being repeated by different people because they have no idea that other people already did them and failed. Mm-hmm. Now, it gets even worse than that because by pure chance, somebody might do a failed experiment and get a positive result. That's just normal variation in reality. So if somebody does an experiment that has been done before and been done multiple times before, but didn't pan out, and then they happen to be the 5% person who gets a positive result, now they might publish that result because you can only publish positive results mostly in the ecosystem with publication culture. And now that false finding is in the literature, and now anybody might decide to build upon it. So all these problems have sort of been known to exist, but only in the past 10 to 15 years have these big, large-scale replication projects come out where people will take like 10, 20, 30, 50 studies and they'll replicate all of them. This is across, tens or hundreds of labs, like tons of people pool their resources to replicate experiments from the literature. And they've been done in psychology, economics, cancer biology, a lot of cases. And the numbers are usually pretty dismal. The effect sizes are around half as large as original studies, somewhere around like 20 to 50, sometimes 60% of them are statistically significant in the same direction. There are different ways to assess the quality of a replication, but in general, it doesn't look very good. And so now that we have all this empirical data that show that all these perverse incentives actually impact how well a lot of science replicates, people are trying to solve the problem. So one example of an institutional measure being taken to fix some of these issues is what's called registered reports. So who I mentioned earlier, Chris Chambers, he was sort of like the champion of this starting in like 2013 or so. And I think they've been adopted by about 350 journals, but just this year, Nature, which is like the creme de la creme journal, started offering them as a publishing model for not all subjects, but I think a few subjects. Mm-hmm. But essentially the way it works is, let's say you're the editor of a journal, I'm a scientist. To you, I don't submit a completed study. I submit the idea for a study, essentially intro and methods. Mm-hmm. So I'm submitting to you my experimental design, what experiments I'm going to do, what controls I'm going to run, the sample sizes, all this stuff. And then if you, the editor, think it's cool, you give that to peer reviewers, not a completed study, just a comprehensive idea for a study. And then me and the peer reviewers iterate back and forth on the details. Maybe this experiment should be added. Maybe you don't need this experiment. Maybe you need to add this other experimental group. All those sorts of things. But then if me and the peer reviewers come to a consensus, you as the editor give me, the scientist, what's called in principle acceptance, which means is that as long as I stick to the plan, as long as I do what we agreed on, I'm guaranteed publication. So the results no longer matter. Publication decisions are now completely disconnected from the quality and character of results, which is really, really great because now you're removing all of the incentives to selectively report experiments, to p-hack, to HARC, all these different things. So that's really important. It's not a panacea. There are many different problems, but I think that is just one example of like an institutional change that would very quickly better the situation. And the proof is in the pudding on this, actually. So a couple of years ago, Anne Scheel and a couple of other people, they published a side-by-side comparison of registered reports and regular papers on similar topics in psychology. And they asked the question, what percentage, found support for the hypothesis? In the regular papers, 96%, because that's generally how science is published. You write your paper as if you had this hypothesis and you found support and we won, and it's great and it's awesome. Well, for the registered reports, it was 44%. Because that might be just what real science looks like. A lot of what we test fails. Science is hard.